Hello, welcome back. This is Calculus by Dr. Oz. Today we have a wonderful application of differentiation. It's called limits at infinity. So this is not only important for the sake of calculus course, but you're going to take a differential equations course probably at some point, and you're going to look at the long-term behavior of the solutions of differential equations. And for that reason, you're going to look at the limit at infinity. So that's why this is an important topic in calculus to be covered for not only, again, serving for calculus, but for other important math courses. And this concept of limits at infinity is going to allow us to investigate if a function has horizontal or slanted asymptotes. So we have three learning objectives to achieve today. And the first one is how to determine limits at infinity. And the second one is how to determine the horizontal asymptotes, if there is any, of the graph of a function. And eventually we're going to determine infinite limits at infinity. So that's going to be a fun series of videos. Let's get started. So I'm going to start off with an example. It's in fact an example of a rational function 3x squared over x squared plus 1. So we're going to talk about the long-term behavior or the and behavior of this function on an infinite interval. So when we talk about that, it's the interval negative infinity and infinity. So essentially, we're looking at the limit as x approaches infinity of f. And secondly, we're going to looking at the limit of f as x approaches negative infinity. So again, in short, this is called the end behavior or long-term behavior of the function. So here's the interactive graph. So our orange dot is moving on the graph, the rational functions graph. And as you see that to the right or to the left, it doesn't matter. So the function values get extremely closer to y equals 3. So that tells us that y equals 3, in fact, is a horizontal asymptote in that regard. We can also see this without a graphing calculator, obviously, by looking at the table of sample values. So as you increase x starting from 0 in this direction and decrease x, obviously, to negative infinity. So my sample values are 1, 10, 100, and you can add 1,000, 10,000, and so on. And you get the symmetric versions of that on the left-hand side as well. And you look at the function values. So you see that the function values get extremely closer to 3 if you go in this direction or in this direction. Okay, so this even table of sample values tells us that the limit as x approaches negative infinity of f is going to be 3. And in the meantime, limit of f as x approaches infinity is exactly equal to 3. So as you see that I have tried different ways of looking at the limit. Uh, the most primitive technique, obviously, is just having the table of sample values. All right, now let's talk about the official definition of limits at infinity. But before doing that, this part is for honors section students. So if you're not an honors section student, disregard only this part of this video that I'm not going to test you on this definition. But if you're an honors student, you're going to be tested on this definition here. And before doing that, let's define what we mean by increasing without a bound. So essentially, when we say like a statement is true as x increases without bound, we essentially mean that for some large number m, the statement is true for all x in the interval, which is consisting of all x's such that x is greater than m. Okay, so what do we mean by saying like the limit of f is exactly equal to L as x approaches infinity? So if L is a real number, okay, what this means is that for each epsilon provided to us, there exists a positive number m depending on epsilon, such that whenever x is greater than that number, f of x minus L in the absolute value is kept in the epsilon neighborhood. And there's a good picture for that. As you see that the graph of f is the curve, black curve here, right? As you see. And then here is the L as a number, right? And we can easily see that the difference between the function values and L is kept in the epsilon neighborhood because this strip here is just epsilon epsilon bigger than L, as you see. So that's strip the top part of that. This is L plus epsilon, and the bottom part of that is L minus epsilon. So essentially L and the function values are kept in that strip. Okay, and then the same definition applies for the limit as x approaches a negative infinity. And what we mean by that is like for each epsilon provided, there exists a negative number depending on epsilon, so that whenever x is less than that capital number n, uh, capital N, so that f of x minus L in the absolute value is kept less than epsilon. Okay, so now for this picture, we are going in this direction because x approaches infinity, but you can have the same thing as x approaches negative infinity if you go in this direction. Okay. All right, this ends the discussion for the first video. We talked about how we can determine limits, finite limits at infinity. And in fact, we had the table of sample values, or we had the graphical aid through your calculator or any other software that you use. So we're done with that. And in the next video, we're going to talk about horizontal asymptotes of graphs, if they have any. So I'll see you in the next video. Bye.